Dear students, this is the fourth video lecture dealing with the shear strength of soils. In the previous lectures, we have dealt with the concepts like Terzi's effective strength concept, Coulomb's concept, Moore's concept, and Moore Coulomb concepts, which prepared us to understand the shear strength in a better fashion. In this session, let us focus on the measurement of the shear strength. Shear strength can be measured in the laboratory as well as in the field. The laboratory tests are performed on representative soil samples and must be done in such a way that represents the field conditions properly. The laboratory shear strength tests are direct shear test, triaxial compression test, unconfined compression test, laboratory vane shear test. Some of the field tests are in situ shear box test and field vane shear tests. Before proceeding with the different test procedures, let us understand the types of the shear strength tests based on the sample drainage conditions. There are three basic types of shear test procedures depending on the sample drainage conditions and can be adopted in case of shear box test and triaxial tests. These are commonly designated by two-letter symbol. The first letter refers to what happens before shear and the second letter refers to the drainage conditions during shear. These tests are unconsolidated undrained test or UU test or undrained or quick test. Second one is the consolidated undrained test or CU test, or it is also called as consolidated quick test. The third one is consolidated drained test or CD test, or it is also called as drained test or slow test. In all these tests, there are two stages. One is consolidation stage, second one is shear stage. In the consolidation stage, a normal stress or a shell pressure is applied to the specimen and is allowed to consolidate. Normal stress is applied in case of box shear test or shell pressure is applied in case of triaxial test. Second one is the shearing stage. In this stage, the shear stress is applied to the specimen to shear it. Let us discuss these three tests in detail. Number 1. Unconsolidated undrained test. The sample is subjected to a specified initial stress, that is normal stress in case of box shear test and all-round pressure or shell pressure in case of triaxial test. And without waiting for any consolidation, shearing process is started without permitting any drainage of the water. Thus, no drainage or dissipation of pore pressure is permitted during either consolidation stage or shearing stage, that is, during the entire test. The results of such test can be used for field problems where critical stress develop in a saturated soil mass too rapidly for any moisture content to change appreciably. Examples: the bearing capacity of the foundations on saturated homogeneous clays. Second is the earth pressure in bracings in temporary excavations. Third is the short-term stability of embankments and earth dams. The second test procedure is consolidated undrained test or CO test. In this type of test, the specimen is allowed to consolidate in the first stage. That is, the specimen is subjected to certain initial stress, that is normal stress or shell pressure, and thereby the pore pressures get developed, and there is sufficient time for these pore pressures to get dissipated, and thus the consolidation of the sample is complete. The drainage is permitted, that is, the drainage is permitted till the consolidation process is complete. In the second stage, when the soil specimen is sheared, it is done so quickly that the pore pressures developed do not have a chance to dissipate, that is, no drainage is permitted during the shearing stage. The test is also called as consolidated quick test, and the field examples are stability of consolidated earth dams under rapid drawdown condition. The third test procedure is the consolidated drained test or CD test. In this type of test, the drainage is permitted in both consolidation and shearing stages. The sample is allowed to consolidate in the first stage. When the consolidation is complete, it is sheared at a very slow rate to ensure that fully drained conditions exist and the excess pore water pressure is zero. The test is also known as drained test or slow test. For example, final bearing capacity of soil where foundation is erected more slowly than the soil consolidates. Now let us discuss the box shear test or shear box test. It is the simplest, oldest and most straightforward method for measuring immediate or short-term shear strength in terms of total stresses. In this test, a sample is placed in a metal box, square in cross section. The size of the box is 6 cm by 6 cm and 2 to 2.5 cm depth. The box has two halves, one upper and another lower, dividing the sample into two equal halves or parts. The sample is prepared in a sampler and then transferred to the box. The box has two grid plates, one each at top and bottom of the soil sample. These are kept in such that the seriations are perpendicular to the direction of the applied load. The filter papers are also used between these grid plates and the soil samples in case of drained tests along with the porous plates. A pressure pad is used to receive the normal load through the hanger. A U-arm is attached to the upper half of the box to transfer the load and is connected to a proving ring for shear load measurement. The assembly is mounted in a larger box with pedestal and resting on the rollers. The entire assembly is mounted on a loading frame. A dial gauge is used to measure the deformations. A normal stress, say 0.5 kg per centimeter square, is applied on the sample through the hanger. In some cases, the vertical movement of the sample is also measured, which indicates the changes in the volume. It helps in evaluating change in the density and void ratio during shearing. The shear stress is applied gradually at a given rate, causing the two halves of the box to move relative to each other. The shear force is applied and corresponding displacement of the box are measured and the shear stress is calculated. The maximum shear stress is noted. The test is repeated on identical samples with different normal stresses, say 1 kg per centimeter square, 1.5 kg per centimeter square, etc., and respective maximum shear stresses are recorded. For performing undrained test, that is UU test, grid plates without perforations are used, while for a drained test, perforated grid plates are adopted. The data is plotted on a graph to a natural scale and a straight line is fitted passing through maximum number of points. Extend the line up to y-axis and the y-intercept is measured, which gives the value of cohesion C. The angle of internal friction is the angle made by this line with the horizontal. Now let us look into the advantages and limitations of direct shear test. There are many advantages. The test procedure is simple, relatively fast, especially for the granular materials. The test setup and the equipment is simple to test the soil under different saturation, drainage and consolidation conditions. The test principle is applicable to the material containing large particles. The recompacted samples are not difficult to prepare. The quick drainage of the pore water in the sample is usually easy to achieve because of the thin depth of the sample. And the limitations are it is difficult to control the drainage conditions. As the pore water pressure cannot be measured, the only total stresses are known. The shear failure plane is predetermined and may not be the weakest one. The shear stress distribution on the failure plane is not uniform. Now let us look into a problem. A direct shear test, when conducted on a remolded sample of sand, gave the following observations at the time of failure. Normal load is 288 newtons, shear load is 173 newtons, the cross-sectional area of the sample is 36 cm square. Determine the angle of internal friction, magnitude and direction of the principal stresses in the zone of the failure. This solution can be done both analytically and the graphically. Analytical solution has been left as an exercise for the students. Now let us discuss the graphical solutions. Now, since the shear load is 173 on the area 36 centimeter square, shear stress is 173 by 36 is 4.8 Newton per centimeter square, that is 48 kilonewton per meter square. Similarly, normal stress is 80 kilonewton per meter square. We know one point on the Morse envelope. Point A with coordinates sigma as to 80 and tau as 48 kilonewton per meter square. Since cohesion equal to 0 for sand, the Moore envelope passes through the origin and through this point A, which is having the coordinates 80 and 48. The slope of the line OM gives the angle of internal friction, which is measured to be 31 degree. Please note that the scale on both the axes, that is along sigma axis and tau axis, are same, so that you can measure the angle with a protractor. In the figure, draw the line AC, which is normal to the envelope OM, which cuts the sigma axis at point C. With C as center and AC as radius, draw the Moore circle C1, which cuts the sigma axis at points B and D. Now, OB gives the major principal stress measuring 163.5 kilonewton per meter square, and OD gives the minor principal stress measuring 53.5 kilonewton per meter square. Now the angle ACB, which is designated as 2 times alpha, this is twice the angle between the failure plane and the major principal plane. Measurement gives 2 alpha equal to 121 degrees or alpha is equal to 60.5 degrees. Since in direct shear test the failure plane is horizontal, the angle made by the major principal plane with the horizontal will be 60.5 degrees. The minor principal plane should be drawn at right angles to the major principal plane. Now you can refer to the figure with the details which you can understand in a better way. Let's see another example. The following results are obtained from a series of drained shear tests on 36 cm square samples of silty clay. Plot the shear strength envelopes and find the shear strength parameters C dash and phi dash. Please note that here, since it is mentioned that it is a drained test, the shear strength parameters are mentioned as C dash and phi dash. The normal stress and shear stress values have been given as 20, 40, 60 and correspondingly 19.5, 28.6 and 38. Now choose a graph sheet, normal scale, and adopt the same scale on both axes. Plot these 3 points and draw a straight line passing through these 3 points or maximum of these 3 points. And you will get a straight line or which represents the strength envelope. Extend it to the y-axis, and y-intercept is the cohesion. That is, cohesion value is 10 kilopascals from the graph sheet. Measure the angle made by the strength envelope with respect to horizontal, and from the graph sheet it works out to be 25 degrees. Dear students, in this session I have discussed the necessary details of direct shear test and few problems. You are advised to practice few more problems for better acquaintance. Thank you.